It's self-weight, right? So the beam supports its own weight. The cross-sectional area is equal to BH, which is equal to 4 times 12, which is 48 square inches. In a 1-foot section, that means there's 48 times 12 cubic inches, which is equal to a number. What's 48 times 12? Got to do them every once in a while. Is 576 cubic inches. Divide that by 12 cubed, right? This gives me, this is in cubic feet per cubic inch. It's going to give me a volume in cubic inches. Is equal to 0.33 cubic feet. Remember what our weight of density of concrete is? How many pounds per cubic foot? 150. So the weight come on, man, paper grows on trees. Lots of it around. Weight is equal to density times the volume, which is equal to 150 pounds per cubic foot, multiplied by 0.33 cubic feet, gives me a load of 50 pounds per linear foot, right? Because I made it 1 foot long. And so my beam is loaded with a uniform load of W, where W is equal to 50 pounds per cubic foot, or per linear foot. And I could walk you through it. The maximum moment occurs at midspan, and it's equal to W L squared over 8. So, I know that my stress is equal to my over I. My I is equal to BH cubed over 12, which is equal to 4 multiplied by 12 cubed divided by 12, which is 4 times 144, which is 556, right? Why do I think that's not right? Oh, a couple of pointers for this class. I will guarantee you, it's 576. I will guarantee you that while up on the board, you can see I work without a net, I will make a calculation error. Those of you who've had me as a professor before know that if you tell me about that calculation error, I'll say, oh shit, sorry about that. Okay? So follow along. You never know. I could be making these calculations errors on purpose to see whether you're paying attention. But it's more likely I make a calculation error. Usually what I do is I use the wrong unit. I go back and instead of the right width or the right length, I use something else. So stop me if I get it wrong, but follow along to catch me. Some of you know, those of you who have had me before, I treat you like you're the construction professionals you're about to be. Right? I work with people like you all the time, and I don't make them call me professor, but don't call me mister, because I didn't go to evil engineering school for 15 years to be called Mr. Right? Try. All right. So there's our moment of inertia. The extreme fiber stress at the bottom, Y, is equal to H over 2, which is equal to 6 inches. My moment, WL squared over 8. W is 50 pounds per linear foot. L is 25 feet, so it's equal to 25 times 12, which is 300 inches squared, divided by 8. And this gives me a load in a moment in pound, right, because this is in pounds, inches, because this is inches squared, and this is, yes, this is in square inches. This is in, yes, gets me pound inches. So if I calculate that number, what do I get? 562,500 pound inches. Sounds like a big scary number, but it's only 56.25 kip inches. That's why we like writing kips. Now I have everything. I can calculate my extreme fiber stress, right? I know my stress is equal to my over I, which is equal to 56.25 kip inches, multiplied by Y, which is 6 inches, divided by 576 inches to the power 4, because those are the units for my moment of inertia. And I'm going to have, up here I'll have kips, inches squared. Just take this to square inches, and I'm going to get a result in kips per square inch. What do I get as my result in kips per square inch? 0.5859 KSI, which is 586 PSI. Thank you. Okay, 586 PSI. That's the tensile stress, the bottom of the beam. Go back to the beginning of our notes. How strong is our 4,000 PSI concrete in tension? 506. Uh-oh. Now, Houston, we have a problem, right? Our demand is 586. Our capacity is 506. What happens to the beam when we remove the forms and supports? It fails. It comes down immediately. But it kills the crew that's stripping it. Because concrete fails in a very frightening way. Did Heath break any samples on the compression machines? So remember, you would take the load, it would look normal, and it would go bang, right? It would all of a sudden be shattered. Now imagine that beam, 50 pounds a linear foot, 25 feet, 15 feet above people's heads while they're taking the forms off, does the same thing. Instant failure. Comes down without warning. Not a very good system, right? We're not going to allow beams to fail suddenly without warning. We're going to design our beams this semester because everybody else in the world does, because no one is a maniac, to tell you there's something wrong with enough time, days usually, for you to do something about it. So do we use reinforced concrete or do we use non-reinforced concrete to span distances? No, because we're not homicidal maniacs. We want to make sure that when we're using our loads, we're not causing a sudden catastrophic failure. And that will be part of our design intent. We don't want to run into this situation ever if we can avoid it. In this case, demand is 586, capacity is 506, demand exceeds capacity, fail. We don't want this to happen, but if it does have to happen, because somebody made a mistake, either in the original calculations, in the erection, or because the loads that are on the structure are not what was anticipated, we want the structure to tell us, hey, stupid, I'm about to fall down, why don't you do something about it? Because if we cut the span in half, put up a single strut at 12.5 feet, what does it do to the moment? Moment gets cut in half, that half part, the L is squared, it cuts it by 4. 586 over 4, now our demand is much lower than our capacity. You can write, if we had it slowly failing and not suddenly failing, you would know you could rush in, put in a post shore, just one. That's all it'll take. Cut the span in half. So that's what we have to cover for today. There's a lot of mathematics involved, you may have noticed. Everybody who loves mathematics, just keep breathing for the next 5 minutes, right? Because we all love mathematics. Let's spend just a moment talking about philosophically how we're going to run this course. None of you intend to be licensed design professionals, at least not without additional training. And so we're going to talk about the code, we're going to talk about how to design beams, because I want you to come away with 3 very important things. Number 1, why when you ask the structural engineer a question, she will always say, I'll get back to you. Because it takes analysis. Even if the computer's doing the analysis, it takes time. So that's number 1. Number 2, to know what a structure looks like when it's in distress. Because most structures that are going to collapse during construction. Either someone puts an unbalanced force on it, which happens, or worse, some idiot designs it, you build it to their design, but they've made a mistake. Okay, and they think you're having a bad 2020. There's 2 corpses still lying in the wreck of that Hard Rock Cafe Hotel in New Orleans. And nobody knows how to get inside the structure safely. They take the corpses out. That's probably the worst 2020 that we're having, right? And they tried to figure, about 3 weeks ago, they were talking about putting a robot in to get them. And I haven't heard anything, which means it didn't work. So you're going to be on construction sites. You're going to see things. And I have a very personal reason for it. I want you to be able to tell the structure is coming down. And I'll tell you what that personal reason is as we go along through the course. The third is, I want you to know when you look at a building, how does it carry the loads in reinforced concrete? Steel is easy, right? Because you can look, or wood, it looks like it's deteriorating. You can see the structural member. But I have no idea how the bars in that column are doing. I'm assuming they're okay. They're inside, shouldn't be anything wrong with them. But I can't go back post facto and repair them. And I looked at some catastrophes on Monday in a place I can't tell you about yet, where people forgot to put in the embedments, the weld plates and connectors. So a $10 problem becomes a $10,000 fix. I forgot to, or I put them in the wrong place. You want to know why can't you just go in and drill new holes? Because you cut the bars. And some of the bars, you can cut them. And some of the bars, you must never cut them. And you need to know the difference so that you don't propose something dumb. The other is, it's always something, everybody knows what VE stands for in construction? Value engineering. Someone says, you can do this, and we can do it this way, and it'll be cheaper than it's been specified, and we'll split the savings. Very common thing to do. You need to know when someone says, hey, if I remove those bars up 2 inches, I could save $10,000. You need to know why that's a really bad idea and be able to tell them. So that's what we're going to work on. We're going to try to go through this class and teach you how to design beams, columns, slabs, footings, post-tension members, and retaining walls. If we don't get it, and as well how to analyze walls, both masonry walls and how to analyze masonry columns, because they're almost the same thing. But if we don't get there till the end, but what we cover gives you an understanding of how to read the plans, then we've solved our mission, right? So that's why I want to do this class face-to-face, so I can see if you're following or not. Because I would rather you understood the things that we covered and got the philosophy behind it than to be able to half design a bunch of stuff but really not know what's going on. Okay? So I will see you next Thursday. Look at that, I didn't get far enough to give you a homework assignment. That's 2 benevolent things in one day. Sorry. They're going to kick me out of the professor club.
Yeah. Why they get out?